as you guys finish grading. For anyone who's referring back to this later, I'll go ahead and go to the beginning of homework because we were talking through lots of stuff. If you need it, pause it. We have 8, 10, 18, 26, 28 and 34, 36, 38. All right, guys, have your questions ready for me. We're just going to go in order from the beginning to the end of homework, okay? 42, 44, 46. 56 was Euler's. 60, 72, 74, and 78. Okay. What page was homework again? All right, we got stamp sheets in. We got test reflections in. Tomorrow you get a new stamp sheet. If I can keep all my logistics straight. Did you already turn it in? You already checked? I'm just saying you can look through the pile if you want. It's up to you. I don't know what to tell you, buddy. Maybe that's a come talk to me. Okay. What's the first homework question? I know it's still coming up. Oh, I'm ready. Where are we going? Anything before 25? Riley, anything before 25? It was probably a matching one, though, right? Yeah, I think it was 41. Okay, let's get 25 first then, and then we'll go ahead and see what's going on. Number 21 gives us, or we're supposed to be looking, I should say, at these graphs over here to the left, A, B, C, and D. Well, this one, these are showing the flow, right? But in the flow, can we conceptualize the slopes? Okay, so for number 25, we know automatically not C or D because it never goes negative, right? Oh, sorry. Yeah, because well, you have to think about the slopes. This is the flow, and so if the slopes, dy dx always refer to slopes, right? R is squared quantity, that would always be positive, and so I need everything whatever point I choose, there must be a positive slope. Well, positive or zero, right? Positive or zero. So then these ones, C and D, are automatically out. Now we have to compare B and A as far as what the difference is. Can you guys tell what the difference is? I see zeros for A somewhere removed from the x equals 0, and for B I see zeros at x equals 0. How does that help me with trig? Sine and cosine, it's all about when the zeros happen. So for sine, the zeros happen at 0, right? So I need the zeros, the flat lines, the leveling off, right? The horizontal tangent lines to happen at x equals 0, therefore B has to go with 25. Whereas this one is probably cosine, right, because it would be removed. Okay, what's another one? Really? Okay, what's the flow? Did you find the other one, Riley?
It was just a lot of the matching ones, like for...
What are other ones you missed? Can you just give me an example?
35 is good, I guess, right? But I didn't know if it was something about if they wanted the differential. I don't know if the graph was up. At the social, they were trying to match it to the differential or to the integral. I don't know.
Like whether or not to be thinking of antiderivatives or baby tangents is my guess. Is that what you're meaning?
And so I just realized that I think it's because they want the graph is of the original function. The flow is the original.
Yeah. Does that make sense? The flow is the original. Which, I mean, these ones are easiest without the pluses or minuses. Because this one I could literally anti-derive. I get 1/2 x squared, so I'm looking for a parabolic flow. Does that make sense?
Yeah, I was like, should I be looking for a line or should I be looking for a graph? And then I was like, oh, it's UIDX. So, yeah.
Does that make sense?
Yeah.
So the antiderivative follows the flow. These are the hard ones because these ones you can't anti-derive. right? Plus or minus is impossible for us to anti-derive because there's no way to properly group with dy and group with dx. So then those are the ones where you just have to be thinking of, well, minus 1, 2 minus 2, 3 minus 3. Think of actual points and quadrants and signs and all that jazz versus the other way around. These ones you could technically anti-derive if you really wanted to. You're going to have an ln and an ln. Anyway, that one ends up being a bit more confusing. I would actually probably instead be thinking about, hey, when x is 0, undefined, when y is 0, flat, when y is 0, undefined, when x is 0, flat. But anyway, sorry, that was following the flow. Was there another section of matching we could peek at? Yeah. Ooh, that one's rough because all the slopes are positive, right? Let me take a picture of these. That way we can look at the graphs a little bit more particularly. This is where it gets rough, is when they're super similar, kind of like the y minus x and x minus y of the ones before. So let me see if I can. Well, you can't for 43 and 44 because of the x and y being added and subtracted. Yeah, that's why I was like, I don't understand. So I did all the other ones and then I came back to that and then I was. So what did you narrow down to? You were able to narrow down, right? To which ones? I finished the other ones for 41, 42, 45, 46. Okay. What I see, and I know that doesn't necessarily help you guys, but maybe it kind of can. What I see or what I look for right away whenever I have slopes, I always look for zeros and DNEs just because it's one of the easiest places for my mind to zero in. So right now I know that this one is going to have zeros or flat tangent lines, horizontal tangent lines when x equals y. So I'm thinking of the y equals x line. I need flat. And then this one, y equals negative x. I need flat. That would have been my clue. Because then if I look at this, I'm like, okay, hold on, which one's even moving lines? Aha! Y equals negative x will be 0. So this one must go with 43. And then y equals positive x, 0. Now, technically, you could have taken points like, I don't know, 1, 1, and seen that 1, 1 is 0, and over there 1, 1 is a positive. So which one 1, 1-ish looks 0, and which one 1, 1-ish looks positive? Like, you can do point-by-point analysis. It sometimes takes longer. But when I'm looking at these two graphs, I see a few different things. I see negatives almost entirely in the second quadrant, and I see a mix of positives and flat lines and positives. Like there's a lot of change going on in the second quadrant. This one, not a lot of change over here. So you could think of, if I plug in a negative x and a positive y, which one's not really going to change a lot? A negative x and a positive y. What's the scale of this? Oh, if this is 1, then this is going way out. Oh, sorry, absolute value. I don't know why I didn't see the absolute value. I was so confused for a second. Lo siento. If you have a negative x, like bigger positive numbers, because they're going to add this magnitude, and then the absolute value will make it positive. So I think I would naturally, even from the second quadrant, make that one match, because a negative and a negative is more negative flipped positive. I'm going to have a lot of positive slopes. But I don't know. I would say the easiest for the pluses and minuses are looking at when the zeros occur, and then point-by-point analysis, checking the different quadrants. Are there any other matching sections we wanted to peek at? Was that enough for the idea? Okay. Let's go play with 7-2 then. Can we go back and play with some integrals? I don't know about you guys. Not that this is my happy place, but it's happier than slope fields sometimes. Just to play with integrals. They're little baby puzzles. Every single one, right? We got partway through. Am I forcing you to do mental math on these integrals? No, I'm not. But when you did 7-1 homework, there were some U-sub ones that hopefully didn't take you a lot of work, right? There was like an e to the sine and a nice little cosine waiting. There was I can't think of what else was there. Anyway, nice little u primes were waiting. But why is it didn't rush this third example on Friday? What could be tricky about that third example? What do you have to remember? Yeah, I think you did one super similar to it. What do you have to remember even to be able to approach this? Yeah, don't get tricked by the trig notation. You can think of secant squared as u squared, right? You can think of tangent to the fourth as u to the fourth. True. However, don't you also have to think about their u primes? Okay, so for instance, which u prime looks more useful in this one? Do I want to be thinking about secant u prime of secant tangent or tangent u prime of secant squared? Yeah, right? So if I was to go ahead and do that, can't I just go ahead and say this is going to be 1/5 tangent to the fifth of x plus c? I mean, can't I look at my u as being tangent and my du as being a secant squared dx, in which case this is going to substitute to be quite nice because that's just going to cancel out to be du, and that's u to the fourth. Remember with trig, or even remember with u sub, you don't normally want to bring powers into the u, right? You don't normally want to bring powers into the u. You normally want the u to be quite short and sweet. But just remember, we always have to be thinking about the u prime because these are chain rule problems where there are extra pieces that came about from the chain rule itself. Does that kind of make sense? Okay. So what if I was to give you something like, okay. Is it harder? Kind of. Trying to do this math style. Yeah, you can pull out the 5. Makes it a little bit nicer. I think it's going to end up being 10/3 square root of 3x plus 1, but I might be off on that. I might have done that a little too fast. What would your u be? Yeah, the u is pretty basic, right? As Aryan said, we could just pull the 5 out and not even need to think about it, right? It doesn't need to be considered in the u sub in any way, shape, or form. My dx is going to be, or I should say my du is going to be offset by a 1/3 in order to make that chain rule stick. We can rewrite this integral as 5 integral of u to the negative 1/2 du, but I also need a third, right? I think it turned out okay, yeah? Because then when you go ahead and solve, which, once again, no pressure that you're doing this, but it's going to be u to the positive 1/2 all over 1/2. I'm just going to end up flipping that 1/2 to be a 2. But that one was a little bit taxing mental math. And if you're taking an AP and your brain is tired, hopefully you'd show work on that one, just to make sure. Yeah, as long as it's being multiplied. But can you ever pull out an extra variable? No. Do AB kids always try to pull out random variables? I don't like them. Yay! Don't do that. Ooh. Okay, you guys go. You don't need me. Take your time, show your work. But you're going to have to make a choice. Keep the x bounds the whole way through, or go to u bounds. But it's your choice, right? You get to choose. To go to u's and back to x's, or go to u's and stay in u's. All has to do with what you do with the bounds. And by pulling out, I'm assuming you mean pull out from the fundamental theorem analysis? Yeah. Just because, Aryan, there are a few people that accidentally write the integral way too long. So I was just making sure. You can do either way. Because if you think about it with distribution, you have a big ol' f of b minus f of a. The 2/3 could be chilling and waiting, or it could be distributed. Yeah, you can stick it to the man. But my question is, did you guys go back to x's, or did you use? Ooh. Okay. Okay. We have a mix of both. If you were to go to use and try to stay in use, wouldn't you have to change those bounds, the u of 4 and the u of -1? You establish who u is right over here. And so you could change your top bound to be 4 cubed plus 1 is 65, and -1 cubed plus 1 is 0. So you could have put in bounds. Your functions in terms of u, your differentials in terms of u, now your bounds are in terms of u, and all you have to do is plug in and subtract. That's u bounds in terms of u, which sometimes the AP forces your hand, but what would have been the other way, even though it's straightforward for many of us, but what would have been the other way? Okay, so the other way would have been to actually keep the -1 and the 4, but then be like, uh-oh, they're not x's anymore. And then you could go ahead and go back to x's, so you'd have, what, 2/15 times your x cubed plus 1 to the 5th. But wouldn't that end up being 65 and -0, sorry, 0? Cross off your bounds because technically it's illegal to anti-derive in terms of u with x bounds. Does that make sense? But then either way you go, you should end up with the final answer of 2/15, 65 to the 5th. Right? I'm looking at both of them. Could you have made it 65 to the 4th and another 65 and reduced with the 15? 15 wouldn't go in nicely though, right? No. So it would still be messy. But I guess the other variation of it could have been 2/3 times 65 to the 4th, and 5 would have gone in 13 times, that'd be 26. That's awkward though. If I would have pulled out a 65 and reduced, it still wouldn't have, it wouldn't have made that nice, so I don't think that would have been helpful. I don't think you guys need me to do this then, right? U bounds, I was just going to go ahead and solve it with x's and then solve it with u's. But u bounds just lets you go straight to the 0.65 du. That way you have a nice little in terms of u, and then your little integrand of u. So you can go ahead and do antiderivative of 65 minus antiderivative of 0. This just doesn't make you go back to x's, but you had to deal with those x's up here. So you're dealing with the exact same math either way. It's just as to when you deal with it, how you answer. We've dealt with this one enough. It technically comes up in this section like, hey, it's a rule. And you're like, no way, we've been using it already. Anyway, u to the n plus 1 over n plus 1 plus c. We have other ones. And here's one that will be particularly helpful for your chapter 6 test corrections. Do you see the ones at the bottom? Did you forget some of these? Ah, who's that? We'll get back to him. Anyway, but this guy, he's one from last year that we forgot. The integral of 4 to the x dx is 4 to the x over ln of 4 plus c. Because remember, every integration rule comes from a derivative rule. So the derivative of b to the u is b to the u ln of b times u prime. So then if I just have a b to the u times u prime, or a du, then I must have had a 1 over ln of b back here. With my derivative of b to the u, which I could just name. How could I name that? Well, I'll just rearrange it here for now. It's kind of the idea. We have to offset by the constant. If we just have this, it must have been divided by ln of b. But that's just the behind the scenes. But that one is your forever card, right? I'm not crazy. Yeah. Yeah. But did we ever integrate ln last year? We're going to learn where this comes from when we learn something called integration by parts. We're going to learn where this comes from when we learn integration by parts. And this one, a change of base formula, I could pull out the 1 over ln of a, so it's really this guy within 1 over ln of a. So you could write it down in order to be able to use. You could write it down in order to be able to use, but ultimately we will learn where they came from. So we're not going to make like forever cards out of you just strictly memorizing it. Guys, this homework is going to be due on Wednesday because there's actually quite a bit more for us to go over. Sound good? But maybe you could start tonight? All right, see you guys later. Ariane, what was it?